So, today we will begin with the analysis of mechanisms. So far in the course we have looked at synthesis, basically creating the mechanism, meaning finding the link lengths to achieve a certain performance. Could be motion generation, function generation, dead center synthesis with a particular time ratio, or path generation. Path generation we also looked at, just hitting specific points, or path generation in terms of certain types of coupler curves that you want for the mechanism. So, synthesis is creating the mechanism. Analysis is once you have created the mechanism, figuring out whether it performs the way you intended it to. Okay. And in terms of the analysis, so even though most of the synthesis tasks were related to position, they were related to position and displacement, in the case of analysis in a real life application, you ultimately want to create a real life, if you want to create a mechanism, then you need to know what kind of strengths that the links in the mechanism need to have, which means you need to know the forces that are acting on the mechanism, which means you need to know the accelerations, and you can't find accelerations without finding velocities. You can't find velocities without knowing the position. So, analysis usually follows, you have position analysis, then which will lead to velocity analysis, which will lead to acceleration analysis, and then typically forces, because you need to find inertial forces which are dependent on the accelerations of the links. So, you cannot violate this order. Okay, you cannot try to do an acceleration analysis without first doing the position and velocity analysis. You have to follow that order. So, we will look at some techniques for position, velocity and acceleration analysis. You would have already seen a few of these techniques in the undergraduate course. I will quickly run through some of those just to refresh your memory, and then we will also look at a couple more techniques that will work for some complex mechanisms for which the techniques that you have looked at so far will not work. Okay. So, we will do that. So, typically when you are the position analysis, if you do it analytically, it is typically non-linear. You have seen the equations for even a 4 bar, okay. Lots of cos theta, sin theta, it is a very non-linear equation. It is quite complex in that sense, but graphically it is a lot easier to do. And so, if you take a 4 bar for instance and you know the link lengths. So, for analysis typically you know the link lengths. If you want to do a position analysis and it is a mechanism with 1 degree of freedom, you will need one input variable related to position. So, typically it is an angle. So, you may be given an angle theta 2. So, if I know the link lengths, say R1, R2, R3, R4, then position analysis of a 4 bar is quite easy. So, I take this and I am given input theta 2. Okay. So, for a particular theta 2, so this is my R2 at this theta 2. Okay. Then I know R1, so that also I can mark off. So, this is R1. Okay. And then I take R3, R4, an arc from here, that gives me the location of, so that gives me the position analysis for this 4 bar. So, you know that, so MATLAB has this circ command, right, which basically finds the intersection of these two circles, one with radius r3, one with radius, you give it the center and the radius, okay, and similarly for the other circle, and then it will find the two intersections. So, the other intersection basically will give you the other configuration for this 4 bar. So, the other configuration will be, so for the same input angle, these are my two configurations. Okay. So, one would be theta 4, the other would be theta 4 dash. One is theta 3, the other would be theta 3 dash. Okay, that gives me the two configurations. So, position analysis graphically is easy to do, analytically it is a little bit more involved, but that is where MATLAB helps with this circ command. You do not have to program all the equations for the for constructing the 4 bar. So, we will look at velocity analysis today, and velocity analysis really looks at, we look at the concept of relative motion. Okay. So, the relative motion, when you talk about velocities, again if it is a 1 degree of freedom mechanism, you need one input velocity. Okay. So, the position analysis needs to be complete. You need to know exactly what the configuration is going to be in all the positions in which you want to analyze, do the velocity analysis, because you are going to use in the velocity equations all these, you will need the configuration of the mechanism. Okay. So, if it is analytical, you need theta 2, theta 3, theta 4, that you get from the position analysis, that will be there in the velocity equations. So, in the case of velocity analysis, your inputs, so what you will need to know is r1, r2, r3, r4. In addition, you will need to know theta 2, theta 3, theta 4, okay, for an analytical this thing, or basically the configuration, and you need one input velocity, say omega 2 typically, because this is for a 4 bar, it is a 1 degree of freedom mechanism, you need one angular velocity as input. So, let us look at how we would do this velocity analysis, and it is based on this concept of relative motion. So, let me take this simple case. You have a rigid body, okay, and say you have a point P and a point Q. P and Q are 2 points on a rigid body, okay, that is moving with some angular velocity omega. Okay. So, if I say this is Rp, I denote it, and say this is Rq, I can write Rq as Rp plus R of Q relative to P. Okay. Now, I differentiate this, so with respect to time. So, this is the velocity of Q. So, I can write the velocity of Q as the velocity of P plus the velocity of Q relative to P. Okay. How does that vector change with respect to time. Let us take a body that is pivoted about a point, and I have two points on this. Okay. So, let us say this is moving with omega. RQ is RP, keep doing this. R of Q relative to P. Okay. So, if I take differentiate this, I get velocity of Q, and I can write R of Q as theta Q, let us say theta P. This is RQ e power I theta Q equal to RP e power I theta P plus R of Q slash P. So, if I differentiate this, okay, in this case when it is rotating about a fixed pivot, the distances RP and RQ are constant, right. So, if I differentiate this, I get I RQ e power I theta Q into omega equals I RP e power I theta P into omega plus R Q. Therefore, this will be the velocity of Q relative to P. Therefore, the velocity of Q relative to P is I can write this as RQ minus RP into omega, which is I R Q relative to P omega. Okay. I am clubbing this as RP, this is RQ, because that is okay. So, what this tells me is if the 2 points are on the same rigid body, then the relative velocity, sometimes some books call this the velocity difference if they are 2 points on the same rigid body. Relative velocity, or the velocity of Q relative to P, okay, is given by this. It is the radius vector scaled by omega and rotated in the direction of omega by 90 degrees. That is my velocity vector. Okay. So, this implies the radius vector, the relative position vector R Q relative to P is rotated in the direction of omega. Okay. If omega is positive, it will be a counterclockwise rotation. If omega is negative, it will be a clockwise rotation, is rotated in the direction of omega by 90 degrees. Okay. This is what we will use when we look at the velocity diagram. So, what this means? Okay. So, this means that the velocity vector, so if this is Q, this is P, okay. The velocity, so omega is counterclockwise like this, in which case this is the direction of velocity of Q relative to P. Okay. What this tells you is, See, these are 2 points on a rigid body, they cannot move closer to each other. The only sort of motion they can have is one rotating about the other. That is what this is establishing, right, because there can be no component of velocity along the radius vector, because that would mean that you are violating the rigid body principle. So, now we will look at using this relative velocity concept to analyze a 4 bar mechanism. So, let us do the graphical method, we will do a few different methods. So, let us start with this you should be familiar with, but just to refresh your memory I will do this. So, you have A, B and you have point P. In fact, from now on I will refer to these two as O2 and O4. So, if this is linked to 2, 3, 4, O2 is the pivot, fixed pivot for link 2, O4 is the fixed pivot for link 4. Okay. We will also denote. So, when I talk about a particular point, I will also indicate which body it is on, because now you have multiple interconnected bodies. Okay. So, when I talk about the velocity of A, I will say I will talk about the velocity of A on body 2, that will be the notation that I use. Okay. So, let us say the input angular velocity is omega 2, that is the given angular velocity, and your task is to find out the velocities of all the other links. So, when we say velocities of other links, when I say velocity of a rigid body, I am talking about angular velocity. When I say velocity of a point, I am talking about a linear velocity. Okay. So, velocity of a body, a point does not have an angular velocity essentially. Velocity of a body implies the angular velocity, velocity of a point, linear velocity. You cannot talk about the linear velocity of a body unless it is in translation, because different points on the body, if it is in general plane motion, different points will have different linear velocities. If I am able to talk about the linear velocity of a body, the only case is when all the points in the body have the same velocity, which means the body is in translation. Okay. So, velocity of a body. Okay. So, let us say, so if I look at 2 as my rigid body, from what we saw earlier, the velocity of A on body 2 equals the velocity of O on body 2 plus the relative velocity. I am going to leave out the vector notation, because you should know by now that these are vector equations we are writing. Okay. V O2 plus V A2 relative to O2. Now, what is the velocity of O2? It is 0. So, in this case, this relative velocity is actually an absolute velocity. When the velocity is expressed with respect to the ground reference frame, we talk about absolute velocities. So, the velocity of A on body 2, we saw that this is equal to I omega 2 and R2. R2 is my length of link 2. Okay. So, here I have O2A, length is R2, AB equal to R3 and O4B equal to R4. So, this is also equal to, now if I look at body 3, the velocity of A on body 2, because A is common to body 2 and body 3. So, this is also the absolute velocity of A on body 3. So, the only thing I know, the things that I need to find out in my velocity analysis, given omega 2, I want to find omega 3 and omega 4. Okay. We will see whether that will be enough to find the velocity. Essentially, I want to find the velocity of any point on the mechanism. But let me, let us say we want to find omega 3 and omega 4, and whether that will be enough for us to find everything else. Okay. Given omega 2, this is what I want to find. Now, if I look at body 3, okay, I know the velocity of A on body 3. So, let me see if I can relate it to the velocity of B on body 3. So, I can write the velocity of B on body 3 as VB3 equals VA3 plus VB3 with respect to A3. See the notation, it is like A3 cancels out. So, okay, so now in this equation, right now I do not know the velocity of B on body 3. Okay. Here let me just retain the vector notation for now. Okay. Okay. So, velocity of B on body 3, I do not know anything about it right now. Velocity of A on body 3 I know completely. Okay. I know both magnitude and direction, because that is the same as, that is the based on the input velocity, and this one B3 relative to A3. Okay. What do I know about this? These are 2 points on the same rigid body. I do not know the magnitude, because that depends on omega 3, which is still unknown. Okay. So, I do not know the magnitude, but what do I know about the direction? I know it has to be perpendicular to AB. So, I know the direction. So, this is a vector equation, which means I have two scalar equations. If I have one more, if I know one more thing, I should be able to solve this vector equation for two unknowns. Okay. Let us see if I can find something about the velocity of B on body 3. If I look at this, the velocity of B on body 3 is also equal to the velocity of B on body 4, and body 4 is again pivoting about a fixed pivot. Okay. So, I do know the direction. Okay. So, if this is rotating, this is in pure rotation, then B, the velocity of B is going to be perpendicular to O4B. So, I know that. So, I do know, if I go back to this, I do not know the magnitude, because I do not know omega 4, but I do know the direction. So, now this becomes a vector equation that I can solve for two unknowns. Okay. So, let us do that graphically. So, let us take in the velocity diagram, all the points with velocity 0 are represented as O. Okay. Now, here this is the vector equation I am trying to solve. This is the one that is completely known, velocity of A on body 3, and I know that it is an absolute velocity, because it is with respect to one of the fixed pivots. Okay. So, I know that it is with, so it will start from O, the velocity vector. So, I know that velocity of A3 is going to be perpendicular to O2A, and it will be of magnitude omega 2 into R2. Okay. So, I know that vector completely. So, I transfer that, that is my vector here. So, this, so in the velocity diagram, the points are indicated by lowercase. So, A will be, and you can put A on body 2, A on body 3. Okay. Now, velocity of B on body 3, again B which is equal to the velocity of B on body 4, which is equal to velocity of O4 plus velocity of B4 with respect to O4, relative to O4. So, because this is 0, again the relative velocity is the absolute velocity, which means I draw this from the point O, because it is with reference to O4, which also has velocity 0. So, if I look at, I know that it is perpendicular to O4B, okay, but I do not know in which direction, because omega 4 could be positive or negative, okay, but I know that it lies along that line and it is an absolute velocity, which means it has to pass through O. So, I transfer that line over here. So, this is a line that is perpendicular to O4B. This here, the input, this is perpendicular to O2A, as I have shown there. Then the third one is, so I have to solve this equation. I need velocity of A on body 3 plus a vector, this relative vector, relative velocity vector should be equal to O4, velocity of B on body 3. So, if I do that, now this is a relative velocity for which I know the direction, again I do not know the magnitude. So, if I look at AB, I know that this should be perpendicular to AB, again I do not know in which way. Okay. So, now, and this will start from where? From O or from A? It has to start from A, because it is relative to A. So, now I transfer this to this point. So, the intersection of these two gives me the point B, B on body 3, which is also equal to B on body 4. Okay. So, in my velocity diagram, now I have basically solved this vector equation. Okay. So, now directions I have, so OA in the velocity diagram represents velocity of A. Okay. Or in this equation, velocity of A on body 3, this direction. Velocity of, so this plus this, if I put the arrow like that, okay, this plus this should give me this, that is my equation here. Okay. So, I will just draw that bigger. So, I have O, A and B. This is my this is just this magnified. So, this is O, A, B. So, the direction of this, in order to satisfy this equation, right, should be this plus this equal to this vector addition. Okay. So, what does this tell me now? Now, from here OB is the velocity of B on body 3, which is equal to the velocity of B on body 4. Therefore, my omega 4 equals the magnitude of OB divided by O4B or R4. Okay. And what would be the direction? Look here. Here from this vector equation I found that the direction is like this, which means what will be the direction of omega? Omega is counterclockwise. It is like this. So, it is counterclockwise. Okay. Because O4B has been rotated in this direction to give counterclockwise to give you this vector. Similarly, if you look at omega 3, from this diagram I have mod AB by R3, if this is R3, R2, R4. Okay. And what would be the direction of this? So, AB here it shows it is like this, right. So, B relative to A is in this direction, which means again omega 3 is also counterclockwise. Now, suppose, so in many cases, so for instance, if this was the solution that I got for a path generation problem and I was really interested in the velocity of P, okay. Why not take P straight away? P is also a point on link 3, right. So, instead of going through B, what if I had taken, so if P is what I want, if the velocity of P is what I want, why not take that directly? Suppose I had written that as velocity of P on body 3 equal to velocity of A on body 3 plus velocity of P on body 3 relative to A3. Perfectly valid equation. I could have tried to solve this directly. Again, I know both magnitude and direction of this. Here again I do not know the magnitude, but I know the direction of both are points on the same rigid body. In this case, with P I neither know the magnitude nor do I know the direction. So, when I am looking at this, I have to look at another point on the same link about which something is known in order to be able to solve this. So, you can't do that directly, but now once I determine omega 3 and omega 4, what is the once I determine, once omega 3, omega 4 are known, then it is easy for me to find the velocity of P, because I just use the same equation plus I omega 3 into AP. That is it. So, I know this completely, I know this completely. So, if I go back to my diagram, let me just copy this over. So, here I should probably, I will rescale this and draw because it is too small. So, I have O, because I can choose any scale for my velocity diagram as long as I know what that scale is. Okay. Okay. So, this is my B, this is my A. Okay. So, now I have, if I want to find the velocity of P, I have the velocity of A plus what would be the direction of this one? This will be omega times AP, and I found that omega 3 is counterclockwise. So, this would be the, and it would be a relative velocity, right. So, from A I would lay off this vector, that does not look like it is. A, B sort of perpendicular, that is because this one is not very. So, this vector, so this denotes point P. Okay. So, now I have the absolute velocity of point P will be this vector, this is P relative to A. And so, similarly, so once I know the angular velocity of any link and I know the velocity of one point on that link, I can find the velocity of every other point that is on the link. So, therefore, once I know the angular velocities of the 3 links, because I know, because these are fixed pivots, from there I can find the velocity of any point on the mechanism. So, this is perpendicular to AP. We get the directions from the vector equations for the omegas. So, that is done. So, we can do the same thing with a slider crank. So, I have O2, AB, 1, 2, 3 and 4. Okay. Again, position analysis is easy graphically. If I know theta 2, I know the path, right. So, I can and I know theta, I know R3. So, I can indicate where on the path it will intersect. Okay. So, here I know R2, R3 input theta 2 for the position analysis. I know the path direction also, and then for the velocity analysis, position analysis complete. Input may be omega 2. It could also be the velocity of the slider, as in the case of an IC engine, for instance. Okay, the input you could be driving it from the slider. So, your input is omega 2. So, let us do the velocity analysis for this. Again, I look at this link. I have velocity of A on body 2 is the same as the velocity of A on body 3, and it equals I omega 2 into R2. Okay, because it is an absolute velocity with respect to O2, which has velocity 0. Now, if I consider body 3, I consider point B and A. So, I have velocity of B on body 3 equals velocity of A on body 3 plus velocity of A3. Okay. So, in my velocity diagram, I have O, which represents O2 fixed point with 0 velocity. Then I have the known velocity of point this one. So, if I look at this vector equation, velocity of A on body 3 completely known, because that is my based on my input. B3 relative to A3, magnitude is not known, direction is known. and B on body 3, what do I know? I know the direction because it is restricted to move in that direction. So, I do not know the magnitude, but I know the direction. So, these are the unknowns. The unknowns that I will solve for are the magnitude of the slider velocity, because here it is not the angular velocity, it is not, it is moving linearly, okay, and the omega 3 for this connecting rod. These are the two things that I will solve for. So, let us see, I have from here, because omega 2 is counterclockwise, this will be my vector. Okay, let me just take a bigger scale so that I get. So, I will have, this will be point A on the velocity diagram. Then I know that velocity of B, I do not know the magnitude, I know the direction is along, okay, P lies, because it can only move along that direction. Then B relative to A is going to be perpendicular to AB. Okay, B can only move in a circular arc about A, which means the velocity will be perpendicular to AB. So, if I do that, and that has to come from A because it is a relative velocity. So, this becomes point B, intersection of these two. So, now if this is the direction of the velocity of A, this is velocity of A, this will be the velocity of B relative to A, which means this is the velocity of B, where velocity of B on body 4 is the same as the velocity of B on body 3. Okay. So, now from this, from the velocity of B on body A, my omega 3 is magnitude of that divided by AB, the distance AB. And what would be the direction of omega 3 from this diagram? So, it is this, right. So, I have found out that this is the direction, which means omega 3 is clockwise. Case of omega 4, sorry, there is no omega 4, the OB is the velocity of the slider block, linear velocity of the slider block.